All right, so today we're going to talk about a max flow algorithm. It's a really, really cool algorithm, and I chose it to sort of combine two topics. One is, of course, flow, which we've been doing, and I want to refresh our memory a little bit. But two, the analysis is going to use some amortized analysis, uh, kind of on the inside. So I thought it would also be a fun way to practice this. So yeah, my goal for the last couple of weeks is to kind of keep choosing topics that gives us more practice. They're new topics, they're interesting topics, but they're meant to sort of double down or build upon existing topics since we don't really have an opportunity to give out new homework, for brand new things and things like this. I'm not going to try to introduce like dramatically different themes, but maybe try to get more practice with it. We only did one lecture on amortized analysis so far, one lecture on randomized. So we'll do some topics in each and kind of that'll hopefully get you some practice. So, okay. So push-relabel max flow. Again, it's an example of amortized analysis. Here are some slides from that lecture. Potential method, Baker method, a banker method, things like this, doubling tricks, so on and so forth. So you've had a little bit of an acquaintance from hopefully starting the homework by now. Okay, so these will also be the fastest algorithms we'll see for flow in this class. So I guess if on the test you can cite certain running times that will come up today. They're not the fastest ever, but it's the best we'll see. So okay. All right, so just to remind us, this is the flow algorithm that we sort of last saw. This was the Edmonds-Karp algorithm, where each iteration you take the shortest path from S to T and you route as much flow as possible. And there we showed that sort of curiously, by focusing on the distances from the source in a residual graph, you're able to get an overall bound on the running time. Right? So that was pretty neat. And yeah, so I just want to make this point because actually this is going to motivate this push-relabel algorithm a lot. The push-relabel algorithm is going to sort of maintain some kind of proxies for distances and some kind of proxy of a residual graph, and it's almost going to be working in a dual space where it's almost focusing on these distances or levels. So that's what the label is going to refer to. Good. So, push-relabel algorithm. Its individual components are arguably simpler than the other algorithms, although I think it's much more indirect. So, okay, and I'll explain what these terms are. One component is going to be a quote-unquote pre-flow. It's going to be like a relaxation of flows, where actually intermediate vertices can have too much flow going in. Okay, so we're going to relax that. And we're going to have these labels or levels. And so labels and levels are going to be conceptually like distances in a residual graph, but something we'll maintain explicitly. So let me break this down further. So what's a pre-flow? So we're going to be maintaining some assignment of flow to edges, just like in regular flow. So I have some directed graph. And it's going to have two rules. First, we're going to obey the capacity constraints as usual, so I won't send too much flow on any edge. That's not new. Now, the second is slightly different than something we've done before. Okay. Now, in a perfect flow, the net flow in any intermediate vertex should be zero. What goes in is exactly what goes out. But now we're going to relax it so that you can have too much flow going in. So you can have, in this case, 5 units of flow going in, 3 going out. So it's positive 2. There's kind of 2 units of flow sitting here that we haven't figured out what to do with. Okay. And we're going to be working with an algorithm that at an intermediate stage is only going to have a pre-flow. At the end, it will get a complete flow. But at an intermediate point in time, you may only have a pre-flow and where you're kind of gradually trying to push more flow one edge at a time. I'll explain more in a moment. Okay. we can have a residual graph just like for flows. We're just, given the flow on an edge, you add capacity in the opposite direction. So that's not new. And anything down here? No. Okay. So good. So the first component is these pre-flows. I think that's a little too small in the top right corner, but that's okay. So the second component, and so this is going to be maybe more dramatically different, is that we're going to be assigning labels to all these vertices. So this is going to be integer values for every vertex. I guess I wrote real valued, but they're going to be integer valued. And we're going to start with the sink always at values 0 and the source always at value n. Okay. And the other rule is that, so every edge in my graph, it can only go down by at most one level. So if I'm here, I cannot go down 2 levels. I can't skip 2 levels. I can only go down 1. Okay. I am allowed to have edges go arbitrarily far backwards. That's fine. But you can only go forwards or down by at most 1 level. You can have edges in a level and things like this. So this will constrain our labels. Okay, so those are the elementary rules, so kind of simple rules, meeting capacity constraints, more flow in than going out, and you have these labels and things like this. So we'll clear up what these mean. So anyway, okay, so right, so okay, one thing is that we're always going to set the source to be level n. And we're going to set the sink to be level 0. So it's like, oh, am I going to have some issues with the edges coming out of the source, jumping too many levels forward? Okay. But to address that, the first step of the algorithm is going to take the source, which may have some edges, okay, and it's going to try to push out as much flow as possible. Okay, so it's just going to saturate all of those edges. So if this source edge had like 10 and 2 and 4, it'll just send 10 units, 2 units, and 4 right away, just as much as possible. Okay. So in the residual graph, these will all be going backwards to S. There'll be no edges going out of S. Okay. And so you're not breaking any of your constraints. So initially, you're probably going to have the source at 0, and then you're going to set all the other vertices to level 0. Okay, so this picture is slightly misleading since there's all these pictures. So initially, all the vertices will be like here, and all the edges will just be kind of around here, plus a couple edges going back to the source. Those are reverse edges. Okay, so, right, it's a little bit abstract. We're going to clarify what's going on with a few lemmas, but you're maintaining something that looks like a flow. It's a pre-flow. Okay, so you're still putting flow on edges. You're meeting capacity constraints, but you don't have to make sure middle vertices are allowed to have extra flow. Okay, the high level idea is that our first step, we're just going to push out as much flow from the source as possible. Right? We're trying to get all the flow to the sink. That's of course an upper bound because that's the cut at the source. And so one by one, we're going to pick a vertex with too much flow and try to push it, try to push it, try to push it. Okay. So, okay. So we're going to say a vertex somewhere in the middle is active if it has positive net flow. So I guess I'm using f hat u to be like, oh, what's the net surplus at that vertex? Okay, so given f, hat f of u is going to be the amount of flow going into u minus the flow going out of u. It'll always be non-negative. If it's positive, I'll call it active. So these are vertices where, I just want to keep pushing flow out of and making progress. And yeah, so the high level goal is to take all these active vertices that have too much flow, right? We want to make sure there's no intermediate flow by the end. We're going to just try to push flow out onto other vertices and hopefully gradually push it into the sink over time. So, right. So we're going to do that with only two operations which give the name. So the first step is you select. So given an active vertex U, you have two steps. You have only two choices. One is that you can push flow out of U in the forwards direction. So the sink is always level 0. The source is kind of way up at, oh, for U is level 0 here? Sorry. 0, 1, 2, 3, and no, 0, 1, okay, good. Okay, I reverse myself. Okay, 0, 1, 2, 3, 4, 5, N, right? So the sink's over here. The source is over here. Okay, sink is always at level 0 for us. And I have some vertex somewhere in the middle. It has too much flow. Ideally, I want to route the flow to the sink. So I'm going to try to push it down a level, down a level, down a level. So I'll pick a vertex with too much flow, see if I can push it down a level. I'm trying to push the flow towards the sink. Okay. Or, we'll have a demo to kind of go through this. Or I have a vertex that has too much flow, it's somewhere in the middle, and there are no forwards edges. There are edges, but there's no way to go forward, right? So if there's no forward edges, then I can actually take my vertex and go up one step, and it won't violate my constraint. My main labeling constraint is I can't have any forward edges go 2 levels, right? But if there's no edge going forward by 1, then after I go up by 1, some edge might go up, down by 1, but not down by 2. Okay, so that is the other constraint operation. So you try to push flow along a forward edge if there is one, and then you might as well push as much as possible. I think all the algorithms we'll see today will push as much as possible. And if you can't find a forward edge, then you can relabel the vertex to a higher level. Okay, so maybe over time, that vertex might even end up on the other side of the source. It might get to level n+1 or something, and then you can push flow back into the source. Okay. So, good. So, right. Okay, so here are the two operations. I guess what I did physically, I've also written out. So, in the picture, you have this vertex U. It has too much flow. You find a forward edge. You push it to V. Okay. And we will push as much flow as possible, which will either be restrained by the amount of capacity on that edge, or residual capacity, because you're in some residual graph, or the excess flow at that vertex. So if this flow has only 5 units of extra, this vertex has 5 units of flow, I can only send 5 units. But otherwise, I'll send as much as possible. Okay, so that makes sense. And I guess in detail, when we're relabeling a vertex to a higher level, the key point is that if I have some vertex U that's active, has too much flow, and I can't find a forward edge, then it's safe to relabel. I can go up a label and I won't introduce any violations to this sort of distance constraint or label constraint that says that no edge should go forward by more than 1 level. Okay, so if there is no forward edge, then there's no risk when I promote it by 1. Okay, so those are the two steps. Okay, so arguably this algorithm, it's not at all obvious what's going on. It's not clear that it works. It's not clear that it terminates. It's not clear that it gets a max flow. There's lots of questions about this algorithm. But if you're coding it, it's pretty simple. Right? The operations at play are very simple. Instead of like finding a whole path and sending flow along a path, you're just sending flow along one edge at a time, or you're bumping things up. Okay? In fact, this algorithm has a reputation for being very performant in practice, maybe because the elementary operations are so simple. You don't have to traverse a whole graph to send some minuscule amount of flow and things like this. Okay. All right, so good. All right, so you should have lots of questions about this algorithm, right? So some questions might be, do you ever get to a flow? Right, we're doing this pre-flow thing where all these intermediate vertices have extra flow. And your goal is to compute a max flow. So for one, it needs to be a flow. It needs to get rid of this excess flow. We need to figure out how to address this. Okay. Second, WTF. What's the running time of this algorithm? Is it even polynomial? Right? Sorry. Yeah. Yes. Yeah. Yeah. An active vertex is any vertex with positive flow besides the source and sink. Yeah. Which you don't really count. Um, so second, is there a bound on the running time? Could you just make these little baby steps forever? You can see it trying to push flow to the sink, but you push some flow, you go up a level, you push some flow, you go up a level. It's not clear you make progress, right? Um, and there was a third question. Oh, yeah, okay, does it even terminate? Okay, so these are the questions to address. Okay, otherwise it is kind of a neat algorithm though. It's like a very local algorithm, things like this, right? So maybe intuitively something to keep in mind is that somewhere the labels must be important. Because if I'm just pushing flow along one edge at a time in no particular organized fashion, then clearly you could just go around and around in a cycle and things like this, right? So somewhere there's labels and the fact that we're only pushing flow along forward edges and things like this will have to play a prominent role. Okay, so I have created a demo on our favorite silly graph. Uh, so here's a graph. Yeah. Yeah. So there's still many here, strategies within this general framework. So you can try to pick the vertex with the most excess flow. You can try to pick like the vertex that will let you push the most possible flow, which takes into consideration both the excess at the vertex and the residual capacity of the edge. You could try to pick the highest up vertex. You might think that's a good strategy, the closest to the source. You can pick the one closest to the sink from the bottom, things like this. So, yeah, there are different approaches. So in fact, what we're going to do first is we're going to analyze this algorithm without worrying about particular strategies, okay? And then we'll show that some strategies actually do better than others, or at least get better bounds than others, which will be fun. So actually, we'll probably look at least two, maybe three different analyses in this framework. Okay, so yeah, so just to get a sense, because I realize this algorithm is very abstract and things like this. So I've set up 6 levels for a simple graph. Okay, and then we're going to try to make this work. So let's see, did I make these? Maybe I can make this a little bigger. Oh, okay, so there's 4 dots for the 4 vertices all at level 0. Okay, and the first step of the algorithm is to push things up to level n and push as much flow as possible. So what that's going to do, how should I do this? Maybe I'll use red. Okay, so we're going to send 200 units of flow and 100 units out of S. Okay. And so in our residual graph, what we're going to have? We're going to have these backwards edges of capacity 200 and capacity 100. I have an edge from X to Y, capacity 1. I have a vertex from X to T of capacity 100, a edge from Y to T of capacity 100. And then X has, That's absolutely correct. Y to t is 200, and y has 100 extra units of flow. So that's our initial configuration. So now, I'm going to just have you pick out an active vertex and then have you run the algorithm, and I'll just update the picture. Okay. So from here, the algorithm is going to pick an active vertex. Any vertex with positive flow, and look for either a forward edge and push flow along it, or it's going to lift the vertex up by one level. Okay, so pick an active vertex. Y. Okay, so we pick Y, and then we either push flow or we relabel it. All right, we have to relabel because it's already on level 0, so there's no forward edges. So that will go up a level. I'll redraw some of these edges. 1, 200, 100. Okay, good. So now Y has level 1. Okay, now pick an active vertex. Sure, we'll pick Y, and you either find a forward edge, or and push, or you relabel it. Okay, forward edge. So there's a forward edge from Y to T, and how much flow do we push? We'll push 100. So let me update that. So if I push 100 units of flow from Y to T, now T has 100 units, and Y is down to 0 units of flow, and then we have forwards and backwards edges of capacity 100 each. So now we have, in the original graph, we're sending 100 units of flow from Y to T. Okay. All right, so good. So now you get to pick an active vertex again. X, okay, and so X, either push flow or you relabel. Relabel. So it's at level 0, you can't do much. So redraw all these edges. Someday we'll have the technology to do this better. 100, 1, and X has 200 units of flow. Okay, good. All right, pick an active vertex. I will wait until someone picks an active vertex. All right, X, and you either push flow or you relabel it. Okay, push. So there's one edge from X to T. So we'll send one as much flow as possible. That's 100. Okay, that will become a backwards edge. And now T has 200 units of flow. Okay, did I do that correctly? Okay. There was, in the old days, people actually used to, like the first bipartite matching algorithm actually was like from 120 years ago or something, so well before computers. And they were actually trying to solve assignment problems, and they would do it on paper. It's pretty amazing. Okay. So their running times really matter because it's how much time you waste writing. Okay. Um, good. I think this is our intermediate stage if I haven't made any mistakes. So now you pick an active vertex. All right, we'll promote X because it doesn't have any forward edges. To redraw a bunch of stuff again. Right, so I want to point out that this edge that seems to be jumping 2 layers, that's okay because it's in the backwards direction. There's only a constraint on how far forward you can go. Okay, good. So we promoted X, pick an active vertex, X, and then relabel our push. Okay, we can push 1 unit of flow this way. So, okay. So this will become a 9. This will be a 1 edge backwards of capacity 1. Y will have 1 unit of flow. X will have 99 units of flow. Okay. Okay, cool. All right, push or relabel. Pick an active vertex. Push at Y. Okay, so I'm going to push 1 unit of flow from Y. That 100 will become 101. T will become 201. Okay. Uh, what a waste of time. This becomes 99 and 101, like this. Okay. So good. You already pushed 201 units of flow into T. That's sort of one thing you wanted, right? But we're not done yet. If you look at this top diagram, you don't have full flow. So, all right. So pick an active vertex. We'll promote X. Yeah. Should I draw it for effect? So you promote X once, right? It goes like this. And then you promote X again. No, don't bring that. Promote X again. Um, right? And then you promote X. You promote X again. Um, okay, so let me bring these numbers with us. Okay, so now what? Oh, jeez. Yes, I think this number. Yeah, so now you can finally push the 99 units of flow back from X into S. So that'll disappear. This will be some 99. This will become 101. This will update slightly. This will become 101. This will become 99 or something. Okay. And if you look up and to the left, we have our max flow. What it's also neat, so usually to certify a max flow, you need a min cut, right? Okay, so I claim that from this setting, you can also read off the min cut, min ST cut, just looking at the bottom diagram. Or what is the min ST cut in our graph? Yeah, it has S and X on one side, Y and T on the other. The cut has size 201. We have a float of. Yeah, so actually one thing you might notice is that Y and T are on the right, S and X are on the left, right? So that's one hint. And one also interesting thing is that we have these empty levels in between, right? So by the time we terminate, we found some empty level. And I know that there's no forward edge that can jump 2 layers, right? So if I look at just this empty, if I just look at this empty layer here, just the existence of an empty layer, right? I know that somehow 201 units of flow got in on the right, and there's no, this is now the residual graph of a flow, right? And the empty layer tells me, oh, okay, then I know that there's no edge from before the empty layer going to after the empty layer because no edge can jump to. So the empty layer also gives me an ST cut. Okay, as long as the empty layer is somewhere between S and T. Okay, so that's pretty cool. I guess. I don't know. All right, so what you can sort of see is these labels and moving these vertices along labels, they're trying to find the ST cut. Okay, so this is almost like a dual algorithm compared to before. It seems like it's trying to find the ST cut at least as aggressively as it's trying to find the ST flow. Okay. Yeah. No. No, there isn't. Yeah. Yes. Yeah, because there's no forward edge. Right. So at this stage, any empty layer will give you a good ST cut. So even if there was like pockets. Yeah. But we'll formalize. Yeah. I think the answer is no. And we'll formalize this. We'll do a lemma showing, oh, if you find an empty layer. Yeah. So I think it doesn't care if there's more than one, but it'll be clear when we do the lemma. Which might be Friday. Okay. Yeah. I guess that's what they will have to mean. So let's say there's vertices here, empty layer, vertices, empty layer, S. And I think our lemma will be that any empty layer, if you take the T side for one side of the cut and the other side for the source side of the cut, that will be a minimum ST cut. So if you had like two different choices of layers, then you would have two ST cuts that both must be minimum, most must be the same value. Probably don't want to take three because then you're just going to be taking more edges than necessary because it might be completely different sets of edges. In which case, you could be outputting a cut that has two times the size of minimum ST cut because you're just outputting two disjoint ST cuts. Yeah. Yeah. Even in our Fulkerson algorithm from before, uh, all you're looking for is discontinuities in the residual graph. And for simplicity, I said, oh, start from the source and just see what you can reach and take that to be one side of the cut. You could have also started from the sink and said, oh, get all the vertices that can reach me. That'll be one side of the cut. And those could be two different things, right? And in general, you can kind of glob together different components. Yeah. So it wasn't really emphasized, but there's always been more than one minimum ST cut, possibly. Okay. So, so that'll give you a little bit of intuition for the algorithm. But again, we've sort of seen, at least in one very, very simple example, that these things turned out okay. But we don't really know yet. So, okay. All right. So, the first thing to address is, what the hell is a preflow? So here's the claim then. So a preflow, again, you satisfy the capacity constraints, but you're allowed to leave extra flow at various vertices. Okay. And so one way to get a bit of a handle is to say that, okay, so let's say that I have some preflow F, and I'm trying to get to T. Okay, but it's not like a complete flow. There might be some pass all the way, but there's other things that drop off and things like this. So in this simple picture, let's say this represents 1 unit of flow, 1 unit of flow. This would be 2 units of flow, kind of along that path. This will be 3 units of flow, 1 unit of flow, 1 unit of flow, 5 units of flow, something like this at some intermediate point. So you have 1 extra unit of flow there, 1 extra unit of flow there, 1 extra unit of flow there, 1 extra unit of flow there. So it's a pre-flow because there's some other vertices that have too much flow. Okay. So the claim is that I can break this down into a family of paths that satisfy the capacity constraints, some kind of path packing. Okay. But usually we only do S to T paths, right? But now I'm claiming, okay, it'll be like a combination of S and V for different vertices V. But I'll guarantee that I can break it down into paths so that there'll be one path ending at this vertex, one path ending there, one path ending there, one path ending there, one path ending at T. Maybe in the picture that seems obvious, we just need to figure out how to formalize it. So in this picture, you can break this down into 5 paths that satisfy the capacity constraints. 1, 2, 3, 4, 5. Okay. Assuming the flow originally satisfied the capacity constraints, then this collection of paths, there'll be at most 5 edges using these first few edges, things like this. Okay, so the claim is you can always break down the pre-flow into paths. There's a trick proof. How can we argue this? This is a bit like your homework problem, right? Where you were given an ST flow and you showed you could break it down into paths and things like this. And the only annoying part is that now you sort of have many sinks in some sense. Yeah. Yeah, so the easiest thing, you can create a super sink or just directly add edges from all this excess flow to the true sink. Same difference. I'll give these capacities equal to the excess flow. Right? And then I'll think of like extending my flow on these auxiliary edges. Okay. And then you can apply your homework where you can break down this flow in this auxiliary graph into a bunch of S to T paths. It's going to saturate this flow completely. And so you'll get one path that's kind of going through this vertex along this edge. And you remove that edge and that just becomes a path to this vertex. And so everything will meet. Okay, so, right, so good. Okay, so that's one way to build a little bit of intuition around preflows. Okay, is that you can always think of it as sort of like a path, a flow coming out of the source, but it's only the destinations, the sinks that are sort of screwed up. But otherwise, sort of the getting to those excess vertices kind of makes sense. I can find paths to them. Okay, good. So that's how understanding preflows. The next step is to try to understand these labels. So the motivation behind the labels is to act as a sort of proxy for distances. Okay, and this time we'll probably focus more on distance to sink, but that'll come more clear. So here's the claim. The claim is that for any two vertices x and y in the residual graph, they have some distance. It could be positive infinity or something if there's no way to get from x to y. But the claim is that Lx minus Ly is at most a distance from x to y. Okay. Now, there might be some cases where the left-hand side is negative, so it's obvious. But so the interesting case is when Lx is bigger than Ly. Okay. But the claim is that we're always maintaining distances so that Lx minus Ly is at most distance from x to y, where I'm just measuring number of edges to get from x to y. So why is that? Yeah, so it has to do with these. Oh, sorry. Oh, yeah. So remember, the forward edges can only go forwards one level. So if I have some x and I have some y, right, and I'm just looking at the edges to go from x to y, each edge can only go forward one layer, and it could go backwards, forward one layer, forward one layer, forward one layer, right? But here, since in this example, y is at level 1, x is at level 5, so I know that you need at least 4 edges to get from x to y. Could be more because you could be zigzag and stuff, but you need at least 4 edges because each edge can only get you forward one level. So, so this is nice, right? So these mysterious labels, okay, they are to some extent vaguely keeping track of some distances from x to y. Okay, so good. See what's erased here. Okay, so that means that the distance from S to T uh, is always, at least the label of S minus the label of T. And we had fixed the label of S to be N, the label of T to be 0, which is equal to N, right? So what's sort of curious about this when it says that the distance from S to T is at least N? And sort of like why N in particular? Yeah, even better. So distance is counting edges. So there's never a path from S to T in the residual graph. So the algorithm will always maintain this invariant. There's actually no path left from S to T. Okay, so that's kind of neat. Um, good, good, um, good. Okay. So there's no S to T path in the residual graph. That means that I could have always run like breadth first search from S, see what you can reach, and it'll give me an ST cut. Yeah. So the label of, oh, sorry, why is it equal to N? Oh, okay. So the maximum distance is N minus 1. That's N minus 1 edges for any finite path. So as soon as at least N, it's really infinity. So, right. So there's no S to T path in the residual graph. That means at any point in residual graph, there's always an ST cut because S cannot reach T. Right? I mean, I could have always done BFS from S and that would give me some component. The only problem is that these aren't necessarily minimum cuts. So, okay, good. So another way to put this is that, well, sorry, ask again. Yeah. Oh, okay, let me be concrete and let me just focus on this. So that means you're always going to have these empty layers between S and T. So each is a candidate ST cut. Okay. but they're not necessarily minimum ST cuts. Like initially, when you just push all the flow out of S and S is by itself, everyone's on the other side, you're only looking at the singleton cut around S. It's not a very good cut. Okay? But gradually you're going to try to push flow out and you're trying to get better cuts intuitively. Yeah. We're about to get to this point. We're just kind of building these observations up little by little. So if we're not able to at least establish correctness, I can at least present the correctness statement today, and then we'll pick up from there and then mostly do running times next time. So here's one more baby lemma. Uh, if V is active, then the level is at most 2n, right? So you might be worried, this is for the sake of running time, you might be worried about the levels getting bigger, 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 bigger. You know, when does it stop? Right? You keep promoting these vertices. And so the claim is that, well, you'll never get past 2n. Why is that? Yeah. So I think that's the right idea. Let me supply one more bit of information. So I know that, so when a vertex is getting promoted, I know it's active, right? So it has some excess flow. So that means that there must be some path from S to this vertex in my flow, in my preflow, yeah. And yeah, exactly. So when a vertex is about to get relabeled, I know it has extra flow, right? Which means, what you might be worried about. Okay, so in particular, from this lemma, I know that there's some path in my flow where I got that flow from S to V, right? Which is not 100% given just because preflows are so weird, okay? But that is the case here. And so as a result, in my residual graph, I should be able to go in the opposite direction, right? So my residual graph, all these backwards edges are in the graph. So that means for every vertex with excess flow, there's some path backwards from that vertex to S in the residual graph. So if V can get to S, then, its distance is at most n minus 1, so the level can be at most 2n. Right? So we already see this label starting to help us. This rule about only going forward 1 is already saying, oh, there's a maximum on the maximum label, which is obviously going to be helpful for running time's sake. Okay. So since we're out of time, I will mention the lemma that we'll try to prove next time. This will kind of establish why it's correct. Okay. So our claim is that if I can get to a point where F is a flow, okay, then A, it's going to be a max flow. So you have this pre-flow the whole time. And so there's two issues at play. Are you routing a lot of flow to T? And two, is it even feasible, right? Because you have all this extra flow at these intermediate vertices. I'm saying that once you get rid of the intermediate extra flow, the excess, it's already a max flow. Okay, so as soon as your preflow becomes a proper flow, it'll be a max flow. We'll prove that next time. And we'll formalize this argument that an empty layer between S and T will give you a minimum ST cut. Okay, so we'll do that first thing on Friday, and then afterwards we'll get the exact running times, and then we'll finally get to do some amortized stuff as well. Okay, so maybe you can think about this on your own. All right, thank you. Push-relabel algorithm. This is what we started talking about last time, and hopefully we'll finish up today. I think one of the trickier combinatorial algorithms we'll see in this class. And today we'll hopefully get to invoke a little bit of amortized analysis, which was partly my excuse for presenting this. So to remind you, we're looking at a particular kind of flow algorithm uh, that doesn't actually maintain a real flow at any point in time. It's only a pre-flow where intermediate vertices are allowed to have too much flow. Okay? And it's also maintaining these levels, which are perhaps inspired in part by the proof of the Edmonds-Karp theorem, where distances played a role in a residual graph. So, right, push a pre-flow, you satisfy the capacity constraints, but you can have excess flow at a vertex. And these levels are assigning integer values to all the vertices. The sink is always at level 0, and the source is at level n. And the one rule is that a single edge can only go forwards by at most one layer. It can go back arbitrarily far, but it can't jump forward twice. And so the algorithm is somewhat simple, I think. So you find a vertex that has too much flow, and you try to push flow out of it. But you can only push along forward edges. So if you can find an edge that's going forward by one layer, you push as much as you can. And if you can't, then there's no forward edge, so you're actually free to promote yourself by one level. Or is it this way? Wait, which way is S for you? S is over here? Okay, so you can promote yourself one level, and you still won't violate that rule. Okay, so that's that. We even walked through a simulation of this where we kind of, all the four vertices were at 0 at the beginning except for S, and we gradually watched it march up, and the flow eventually got routed into T or routed into S. Okay, and then we started analyzing this a bit. So one thing is that this picture makes it look violent, but if you have a pre-flow, which is in blue here, which has some excess vertices, okay, and this is partly some issue of like what's a pre-flow. You could always think about it as a bunch of paths starting from S but not quite getting to T, all mixed up into flows. Okay, because you can always take this pre-flow and break it up into paths. Okay, so that's one way. Think about it. Now, as far as labels go, and here we start seeing why it's useful to have this whole rule of only going down one level. Okay, so the labels at some level always sort of bound the distance. So the label of x minus the label of y is at most the distance from x to y. Partly because, you know, if y is 5 edges away from x, you can only go down one level with each edge. Okay, so they can only be 5 levels away, at least in the downwards direction. And so that starts getting you some observations. For example, you know that the distance from S to T is n, or is at least n from this bound. But the maximum finite distance is n minus 1. So in our residual graph, we'll never actually have a path from S to T. Okay, so the algorithm always kind of maintains certain ST cuts in the residual graph, not necessarily the optimum one. Okay, and then here was another one that I think we talked about very briefly. So I'll just remind us. The claim is that if you have any active vertex, then the level is at most 2n. And the basic idea is just that if you had a vertex all the way over here at some very high level, and this had some extra flow, okay, we know from that earlier path, from that earlier lemma, that there must be some path in our current preflow going from S to this vertex. Okay, which means that in the residual graph, you must have all the reverse edges. Okay, so that means that any vertex with positive excess should be able to reach S at any moment in time. Okay, and because of this bound on the distances, which I guess I've omitted from the screen, maybe it's up at the top. It's up at the top. so our bounding distances forces the vertices to be at most level 2n minus 1 or something, because it can only be n minus 1 hops away from S. Okay. All right, so why is that useful? Well, one of our goals is to eventually bound the running time of the algorithm. And so one thing you might worry about is how many times can I relabel a vertex going up and up and up and up, right? But now we know that it can only happen at most 2n times per vertex. So we can at least handle that operation, right? So things are starting to come together. Okay, next, and I think this is where we left off. Okay. Okay, so here then is the claim. So our algorithm keeps going until there's no active vertices left. When there's no active vertices left, now it's a flow. The only issue, the only violation ever was these, active intermediate vertices was too much flow. Okay, but you still should ask, is this a maximum flow? And can we find a certifying ST cut? Okay, so, all right, so the claim is, if there are no active vertices, then F is not only a max flow, but I should be able to find some kind of empty layer, right? Some empty layer here that does not have any vertex on it, okay? And if I had taken all the vertices on this side as one side of the cut, and all the vertices on the other side as the other side of the cut, okay? Then this will give me a certifying ST cut. Okay, so we're going to try to argue that the amount of flow we routed, which should all be sitting at T at this point, because there's no other active vertices, should be equal to the capacity of the cut induced by this empty layer. And then you're just done. Okay, so this vertex is just quietly pushing flow just one step at a time. Somehow working down the layers gives it enough of a sense of direction that you're actually making progress. If you didn't have these layers, then you could push, flow around the cycle and never terminate. So somehow these layers are very important towards taking just sort of like very local algorithm and never looks at the whole graph in a single step, and gets it to converge. All right, so I guess this is the key point, key one. So let's try to figure this out. How come if there's an empty layer here, so I guess I've drawn layer I to be empty and maybe there's some vertices on either side. Okay, so there may be edges like this. These are all in the residual graph. And there may be edges backwards. Okay, but the claim is that if I look at everyone on this side as the S side of the cut compared to the other side, this cut should be the minimum ST cut. So these are residual edges, right? So they don't reflect the original edges in the graph. So there were original edges, which I'll draw in purple, right? So they can go very far forward and things like this. They're just in general going forward, but they've disappeared from the residual graph, so that's okay. They don't violate the rules. I'm just saying there may have been original edges going from here to here, but they're now gone, right? How do I know actually that there are no edges from this side to that side left in the residual graph? Yeah, because you only couldn't go down one layer, but because of this buffer, an edge can't go from here to here anymore because it would have to go 2 layers to jump over this river. Okay, so that means that all of these edges in the original graph going from the S side to the sink side have been all used up. We've saturated all of their capacity. Right? Okay, so if this cut had 100 units of capacity, summing up over all these edges, that I know I'm sending at least 100 units of flow. I mean, I'm using them all up, right? So that means, okay, we have some 100 units of flow going from left to right. Okay. Now, this 100 units of flow has to go somewhere, right? So I can think of a few options. It can get deposited at various intermediate vertices, not the T, but that's not the case because or these intermediate vertices aren't active. So this 100 units of flow did not stop at any intermediate vertex. There's two other, so ideally we want to say it's all in T. Maybe one other liability is, okay, I'm sending flow in the original graph across this cut, but maybe I send it back, right? In which case there would be less flow getting into T, okay? I want to argue that this is not possible, but why? How do I know that, again, the blue edges are residual edges, so it's a little bit confusing, but how does this empty layer guarantee that all the flow that's actually being sent from left to right, none of it is being sent backwards? So like, what if you did send a little bit of flow, 3 units of flow from right to left? Your pre-flow is sending flow from right to left. Yeah, so, well, we don't have a notion of active edges. You mean active vertex? That's true. This could be going into S, right? So we're also claiming that none of it's getting sent back to S. So this is an original edge in the graph. Suppose I'm sending 3 units of flow on one of the original edges. What happens to the residual graph? The residual graph would give me a reverse edge. So if I was sending any flow backwards, then the residual graph I would have the exact opposite edge going forwards with capacity 3, right? But what? Yeah, we have this gap. It's impossible to jump the gap. Okay, so we're not sending any flow backwards either. So what do we have? We have an ST cut and some kind of flow where the flow is completely saturating this cut, and all of that flow is getting deposited into the sink. Okay, so we have a flow right now, and we've saturated an ST cut, and the value of the ST cut is equal to the value I'm sending of the flow. So that's it, we're done. This ST cut, the capacity is exactly the amount of flow I'm sending from S to T right now. And they certify each other to be optimal. All right, so that's the idea. Any questions? Okay, so good. So that's the whole algorithm. You just keep choosing the active vertices, pushing flow. When there's none left, you have a max flow. And you can find an empty layer, that'll give you a min ST cut. Now, we know why it's correct. And now is maybe the funner part. Well, I don't know if it's fun or not, but now is a different aspect of, let's just figure out the running time. Okay. So, okay, we already know there's at most like n squared relabels because each vertex can only get relabeled 2n times or something. So we really need to bound the kinds of pushes, and we're going to classify them into two types. The first type of push is what we'll call a saturating push, which well, let's double check, should mean that, okay, good. You are going to use all the capacity of the edge. So if I'm going to try to push as much flow as possible, there's two bottlenecks. One bottleneck is I've used up the entire edge. The other bottleneck is I've used up all the flow at the vertex. Okay. So saturating push is going to mean I use up the entire edge. A non-saturating push means we've instead pushed out all of the excess flow. Okay. If both of them happen, we still call that just a saturating push. Okay. So if we can bound the number of these kinds of operations, then we'll have a polynomial time algorithm. Okay, so that's our approach. So this we already know. The number of really labels is at most n squared. This is again because each vertex can only jump up 2n times. That we've established. Now, the question is, what is the number of saturating pushes? The claim that is that the number of saturating pushes, so I'm here, I'm trying to send flow on this edge, and this edge is limiting how much I can send. So I use up the entire edge. And we're saying that the number of times this can happen is at most mn total, or really, for a particular edge, I can only use it up n times. Well, an edge can reappear, right? So O of m is just once per edge. So edges can I use up the whole edge, it disappears from a residual graph, great, but it can reappear, right? So that's what we want to limit. So let me draw it out. You have some vertex u, v. This has capacity like 2, u has capacity 5. So you end up sending over 2 units of flow. That disappears, and you add a residual edge to the graph. And if later you use the opposite edge, then the original edge will come back. Okay. So I'm trying to argue that each edge I can only use up about n times. How can we argue that I'm only going to, yeah. Perfect. So that edge we first removed can only come back if I push in the opposite direction. Okay? And for me to push along this opposite edge, v is going to have to be on the other side of u, because we only ever push down, right? So level v must go up by at least 2 before the other edge can be even used. Okay? So you put that all together and you say, oh, okay, every time I use up an edge, I can charge it to, v going up 2 levels. V can only go up 2 levels n times. So I can only use up this edge n times. So it's actually very similar to the argument we had before for the Edmonds-Karp algorithm. Okay, good. So number of saturating pushes at most mn. Okay. And now the next claim is that the number of non-saturating pushes is at most mn squared. So here, I have some vertex u. It had some flow. And there was some edge with a lot of capacity, v, and I'm only able to send 2 units of flow. So the claim then is that the number of non-saturating pushes is at most mn squared. I should double check this. But any ideas? Okay, good. This will be fun. Yeah. Oh, okay. So maybe if I had more control over the order in which I pick things, if I'd always picked big things first, then like if I was always doing the highest one, could I argue that okay, you can only do so many saturating pushes before getting at least one non-saturating push? Um, Maybe. I'm not sure, 100% sure how that'll come out. Oh, what if these are super duper? Okay, so okay, I guess we're trying to imagine almost like a worst case kind of thing. You know, okay, I push from you, and then eventually, like you must get more flow. I push from you, you eventually get some flow. And I guess we're trying to argue that, like, eventually I have to, but I don't know. My one concern is what if these are super tiny, 0.0001, 0.000, yeah. Um, it's not super clear to me. Uh, but I do agree that this is believable. Um, okay. Here is uh, here then is this one is a little bit trickier. I don't have as intuitive a one, so we're actually going to use a potential function. Okay. So here's what we're going to do. I'm going to define a potential function phi, where I'm going to sum over all of the active vertices, the level of that vertex. Okay. So uh, for only the active v, I'll sum up the level. Okay, so initially, like this is 0, because all the vertices are at level 0. Okay, but over time, various active vertices are moving up, and so on and so forth. Okay. So, okay, so good. So what we want to do then is we want to bound how the potential changes for each of our three operations. Okay. So take push. Oh, wait, sorry. Let me do relabel first. Suppose I relabel a vertex V. What is our change in potential? Take a vertex, lift it by one label. 1. So now our relabel takes constant amortized time or something, right? Okay. Now what about a saturating push? What's the maximum amount it can go up by? Yeah. Okay, so what's like the worst thing that can happen? So U has positive flow, but V doesn't. V is not active on this edge. So I push flow, but I don't even get to use up all of U. Okay. Um, So I end up just V becomes active, U stays active. So my potential is going to go up because V is now part of the sum. Okay. How much can it go up by? Not 1. It's not 2. Yeah, so how big can level of V be? 2n. Okay. So, and these are the only, okay, and now let's look at non-saturating push. So, a non-saturating push, now you're going to end up using, all of the capacity at U, right? -1. So in the worst case, U has capacity, but V doesn't. So in your sum, it's going to go down by level of U, and it's going to go up by level of V, but you're going down one level. So you at least go down by 1. So, at most -1. Okay. Now, those are the only 3 things that can change our potential. A push or one of the two, or a relabel, right? So what's the total increase? If I don't worry about non-saturating push, which will actually decrease the potential, what's the total increase to phi over the course of the algorithm? Well, there's n squared relabels, so it can go n squared from this guy. And then how many saturating pushes can we have? Mn. So it can go up by mn squared. Okay, so the total increase is at most mn squared. Meanwhile, the potential is always non-negative, and each non-saturating push is going to decrease it by 1. So that tells us that the number of non-saturating pushes can be at most mn squared. All right, so that would be an example of kind of a amortized analysis style argument, but this time sitting in the middle of an algorithm. Okay, so we put that all together, n squared relabels, mn squared, and you end up doing mn squared push relabel operations. Okay. If you're worried about implementing this, all you have to do is kind of keep track of each vertex at each level, and you need to keep track of who's active and who's not. That's not too hard to do. It's just, arrays and lists and things like this. I'm glad you asked. So can we do better? Okay. So can we do better? We did an algorithm that we did not care about which vertex we chose to push. And can we maybe try different strategies to get better bounds? Like, what are some strategies we can try? Largest capacity, most, yeah, vertex. That's one. The one we're actually going to look at, so that does get some bounds. I think we're going to look at the highest label vertex. So one closest to the source, the furthest up, which is almost like you're aggressively trying to pull out that ST cut as fast as possible. Another one that shows up in practice sometimes is the one closest to the sink, the lowest label. Just try to push things into the sink, push things into the sink. Because people actually try these. They also report, different running empirical things for each of these strategies. Yeah. Well, you're gradually pushing flow down, right? Towards the sink, and your goal is to route as much flow as you can to the sink. So you might think, okay, I should pick the active vertex closest to the sink already, hopefully getting it closer by pushing. Yeah. But okay, so what we're going to do is we're going to look at an algorithm where we pick the vertex with the highest label among all active vertices. And we'll see how that plays out. Okay, good. Okay, so for the sake of getting a better running time, the real bottleneck was just these non-saturating pushes, right? These turned out to not be an issue. So we're going to see if we can figure out how to get a better bound on the number of non-saturating pushes. So, okay. All right, so the claim is that if I always pick the vertex with the highest label to push, then there's at most n cubed non-saturating pushes. But why? All right, so there's some level that's like pretty high up. This is the highest one with active vertices. I always pick vertices from here. All right, so let's say this is the vertex of the highest label that it has positive flow, and I push, and I make a non-saturating push, this becomes 0. So it's not active anymore, right? I claim that for this particular vertex, as it gradually makes progress, I can only do a non-saturating push from this vertex and neutralize it at most n squared times. So I had this highest label vertex, and I pushed out all the flow from it. And it won't be active again until it gets some flow. What has to happen between now and then for that highest label vertex to become active again, formerly highest label? It needs to get flow from someone else, but where is that someone else? One of the n-1 vertices, but the remaining vertices all have label less than or equal to this vertex. So in order for this vertex, which used to be the highest label active vertex, to become active again, some other vertex is going to have to get relabeled and carry flow above it. Okay? So for this vertex to ever become active again, some other vertex has to have its label increased. Okay? And what's the maximum number of times that vertices get their label increased? Or overall vertices? N squared. So this can only be reactivated n squared times. For this to be reactivated, at least one other vertex has to be relabeled. So that gets you n cubed total. Okay, n squared per vertex. Okay, good. So now we're down to n cubed. That might be so that's a little bit better. Okay, but we're not done yet. In part because we have time. Okay, and now the question is, can we do even better than a bound of n cubed? Okay, for the same strategy. All right, so we're going to show a bound of n squared square root m which I think is the best bound we'll see for this problem in this class. So the claim is that we can get this down to n squared square root m, which is better than n cubed if the graph is sparse. Right? Because that would be like n to the 2.5 is f, m is m. Okay. So this is tricky. I mean, does anyone want to suggest an idea? This is going to be a little bit denser, but hopefully fun. Okay, so this one is going to be analytically quite clever, but it's going to take advantage of another potential function. So here is what we're going to do. Okay, so for every active vertex, you're going to count the total number of vertices with label less than or equal to it. Okay, so if I went up back to this picture here, up above here, let's say this is active, then you are going to count up the total number of these vertices. Okay, and you're going to add that to the sum. And you're going to do that for every vertex. So now for this one here, you're going to count up all of these vertices. Okay. For amount of colors, this active vertex here, you're going to count up all of these vertices. I guess you actually count itself. So it should be drawn like that. Okay. All right, so that is our somewhat bizarre potential function. So this can be quite big, right? This can be as big as like n squared. If all the vertices are active, and each of the terms contribute n. Okay. Good? Okay, so well, we're going to do something similar to before. We're going to look at the two other operations, say, okay, what's the worst case? How much can it increase my potential? And then try to argue that my non-saturating potentials are going to decrease my potential and then get a bound this way. Same overall strategy, same use of a potential. Okay, so like how much can a relabel increase my potential? We can focus on relabeling first. So I take an active vertex and I relabel it. How much can my potential go up by? It would depend on what? These are already included. So you're counting this. So this one goes up to here. And now you're going to count all of these, right? I mean, there could be some vertices at this level, right? No, it's all vertices. So how many can be on a particular level? N. Yeah. We're just going to write N. And then, good. And so the other one is a saturating push. So if you do a saturating push, right? So you push from this vertex to here, and that vertex, in the worst case, becomes active, right? So then you start adding this number of vertices to the sum. Okay. And what's the upper bound on this? N. Okay, so we're going to use pretty conservative upper bounds here. The cleverness, I mean, yeah, these aren't very like aggressive, right? N seems like very big. It's very generous. In fact, at this point, it's probably not clear why this is a good potential function. All right, so that means over the course of the algorithm, the potential can only go up by so much. Okay, total increase of mn squared. Okay. All right, so now we're going to try to argue that the non-saturating pushes decrease the potential by a lot and get a better bound overall. Okay, so we have to argue that actually it decreases by more than one because we're trying to get this n squared square root m. So, okay. Any ideas? Maybe, probably not. Okay. All right. So suppose you do a non-saturating vertex at V, right? Non-saturating push at a vertex V. So let me erase this. Okay. So you're at this vertex. That's not right. You're at this vertex here that's currently active, right? And the summation is counting the total number of vertices here. Okay. And then when you do a saturating push, then this will no longer become active, but this one might become active. Okay. So let me draw a different color. This one becomes active. So it's going to add this one back into the term. So if you subtract out the yellow, but you add in the purple, then you're going to go down by however many vertices are here. So this one we're actually going to be a little bit more careful and not just bound this by n or 1 or something. So this will always be, the number of vertices at the same level. Okay. So, all right. So, for example, if this is really big, if there's n vertices here, then you're going down by n, right? So that's really great. Or if there's like square root n vertices here, you're going down by square root n. That's also great, right? And you're making a lot of progress on your potential. So, for example, how many times, okay, good. So let's just say like, okay, if there's at least square root n vertices in this top level, then that's really good because I make tons of progress. Otherwise, there's less than square root n vertices, right? But for this particular level, you're just going to keep hitting this until there's no active vertices left, right? How many times can you get a non-saturating push with square root n or less vertices? So let's say there's square root n vertices. I do a non-saturating push, and I delete one, right? Okay, I don't make as much progress on my potential. I literally remove square root n. I wish it was bigger, but that's okay. But now how many active vertices are left in the top level? There was square root n. Now there's square root n minus 1. Okay, so that's 1. And now I move on to the next vertex, this one, and I do a non-saturating push. My potential only goes down by square root n minus 1. Not great. But how many are left? Square root n minus 2. So if I think about like really good non-saturating pushes that decrease my potential by a lot, because say there's at least square root n in the top layer, right? That's great because each time I decrease my potential by at least square root n. Some might even be bigger, right? But the bad case is when I only have a few vertices in the top layer, but the number of times that can happen is limited. If I set that threshold to square root n as an example, that can only happen square root n times. So basically we sort of have really good non-saturating pushes that decrease my potential a lot. That's good because that we just say, oh, the potential can only be so big, and so I can only have so many of these big pushes. Or they're small, I don't make a lot of progress on my potential, but that can only happen so many times because each one is chipping away at it. So that's what we do. We do this kind of threshold style argument, kind of high, low, big or small. So we'll choose some k to be determined. This could be square root n, but what we'll do is we'll just set up like the trade-off and then figure out the best possible k. I'm not sure if it will turn out to be square root n, probably square root m. But the claim is that you're only going to do mn squared over k big pushes and n squared k small pushes. Okay? And if those claims were true, and you want to choose the best possible k for your analysis, what would you choose? Or how would you choose it? Yeah, you want to make these terms equal. There's no sense in having one term dominate the other because you pay for both. So if you set mn squared over k to be equal to n squared k, what should k be? Square root of m. And if you plug that in, you'll get R bound. Okay, so we're going to do this high-low kind of argument, which I don't think we've seen something like this. So this is really saying, okay, I've set up some potential, some quantity, and then I can do this trade-off. Okay, we can do it in 2 minutes. Okay, this one you guys can guess. Why are there at most mn squared over k big pushes? Okay, well, how big can the potential be? Mn squared. And what do I know about these big pushes? They decrease the potential by k, right? By at least k. So this thing is at least k. So mn squared divided by k, each time you decrease by k and you get your bound. Okay, good. So that's that. And now here's the last one, and we're done. Really, we're done. This is all just conclusions. So the claim is that there's at most n squared k small pushes. Okay, so here's what we're going to do. Let's say all the active vertices are at this level, right? And let's define a phase as I stick to a level and I keep pushing, pushing, pushing until there's nothing left at the level. The next highest level probably goes down. Or I relabel and it goes up. So as long as I'm staying on the same level, I'll call that a phase. Okay? Now, how many times can I have a phase where the highest level goes up? N squared, because a vertex can only get relabeled n squared times, right? And now, how many times can you have things where the highest level goes down? Well, ultimately it's n squared. So you can think of it as like an elevator that goes up and down, right? And the total amount, so you're watching an elevator go up and down, up and down, up and down, up and down. And the total number of floors that ever goes up, we know is n squared. So the total number of floors that ever goes down is at most n squared. Okay. All right, so that's one way to say it. And now for a particular phase, so I'm just focusing on one level until that level changes, either up or down. How many small pushes can I have? I guess k, right? Is what you're expecting, but that's because there's only k left, and each one takes one of them away. K minus 1, k minus 2, k minus 3. Down to 0. Okay, so you put that all together, you balance terms, and you get this better running time. Okay, this was supposed to be an example of amortized analysis in the context of flow. So that's it. And next time, I guess we'll do something completely different. All right, thank you.